Property number 4 of DFT is called as the time reversal property. The statement of time reversal property is something like this. If x of n has n point DFT x of k, then x of minus n mod n is equal to x of capital N minus n. This is nothing but application of mod. So these two are said to be equivalent, both are same. Now what will be the DFT of that? In the frequency domain, we obtain the answer, that is capital X of minus k mod n. So if you have time reversal here, in the frequency domain also there is a reversal in terms of frequency. Or this can also be equivalently written as capital X of n minus k. Now, time reversal is called by different names, folding, reflecting, etc. Now, since we are doing it circularly, let's understand the concept first. Now, normally when we do it linearly, the time reversal is folding about the vertical axis. So whatever is on the right will be flipped and will move to the left, and what is on the left will flip and it will go to the right. But here it is slightly different. So let us say the sequence is as given here, 1, 2, 3, 4. We are aware of the shifting operation. So when you shift it x of n minus 1, it's a rotation. When you shift it n minus 2, it's a rotation, that is we are moving two elements to the right and we are bringing it around and adding it at the beginning. So this we are aware of in the case of a shift operation. Now what happens in the case of reversal operation? In the case of reversal, the value at the origin will remain where it is. The rest of the elements are reversed. So the reversal of this will be the values which is 1 followed by 4, 3 and 2. Please remember, the value at the origin will be where it was earlier. The remaining elements happens to be reversed. So this is time reversal. Now let us, so it can also be thought of shifting by n places here. It's one and the same, shifting by n places, or it is a reversal here. Both are the same. Okay. Now let us prove this particular property called as time reversal. Once again, here we start from the definition of the DFT. We are aware that DFT of x of n equals x of k given by summation n between 0 to n minus 1 x of n times wn to the power of k. We are interested in calculating the DFT of x of capital N minus n, which is same as x of minus n mod n. Therefore, substituting for x of n as x of capital N minus n in the definition. Call this as equation 1. In order to simplify this particular equation, we have to substitute the n minus n to be replaced with something else. So here we use a notation called as m. So m is equal to n minus n, and similarly the n will now become capital N minus m, and similarly here also we have to solve for the limits to show the particular change. So the lower limit, which was n is equal to 0, will now become m is equal to capital N on substitution. The upper limit, which was n is equal to capital N minus 1 on substituting in this case, becomes m is equal to n minus the substitution for n is capital N minus 1. So solving here, we get the value as 1. Now let us make all the substitutions. The summation becomes m is equal to capital N to 1. X of m is a replacement for n minus n, wn to the power of k into capital N minus m. So in order to simplify here, yes, the limits we have to correct it so that it looks like our definition. Please observe 1 to n is again n points. Therefore, using periodicity, we change the limit, lower limit to be 0 and upper limit to be n minus 1, because it also defines n points. The total factor is split into two terms, Wn to the power of Kn into Wn to the power of minus Km, which this term we know it to be 1. So since it is equal to 1, you know that term will vanish and you are left with this. Now in this expression, if you observe, everything looks very much like our DFT equation itself, with the difference that in place of k, here we have minus k. So if the previous thing was called as x of k, this obviously should be called as x of minus k. And since we know that everything here is under the control of mod, so that's why we apply x of minus k mod of n. Therefore, we have proved that the DFT of x of n minus n is equal to capital X of minus k mod n, or it is equal to x of capital N minus k. So this property is called as the time reversal property. Let us take a simple numerical. Given x of n is equal to 1, 2, 3, 4 with 4-point DFT, x of k is equal to 10 minus 2 plus 2j minus 2 minus 2 minus 2j. So here they have saved you the trouble of calculating the DFT. They have directly mentioned the sequence as well as its DFT. They ask you to find the 4-point DFT of the sequence, which is y of n is equal to 1, 4, 3, 2. Now here they do not mention which property to use, but carefully observing the two sequence, what we can make out is that the first point is the same 1 and 1, and the rest of the sequence is written in reverse. So we can clearly identify that y of n is a time reverse version of x of n. Therefore, in the solution, observing the sequence x of n and y of n, we find that y of n equals x of minus n mod 4. Now, taking DFT on both sides, what happens? Y of n DFT is called as y of k, and here we need to apply time reversal property. Now we know that when you reverse in the time domain, in the frequency domain also you have to reverse. Therefore, the result is x of minus k mod n, and since the length of sequence is 4, n here is 4, which is same as capital X of 4 minus k. Now, if you are interested to calculate y of k, for k which is 0 to 3, all you have to do is substitute. So when you substitute here, you will automatically get the different values. So start from k is equal to 0, you substitute, first substitution yields x of 4. Now we know that you can have value only 0 to 3. So since it is periodic, we can conclude that x of 4 is same as x of 0. So first answer is 10. Next substitution, k is equal to 1 gives you x of 3. You have the value of x of 3, which is the last term, minus 2 minus 2j. Next, y of 2 gives you x of 2, which is equal to minus 2. Next, y of 3 gives you the answer, which is x of 1, which is equal to minus 2 plus 2j. And finally, you can express the result. The result you got is y of k. It is expressed in this fashion. Now, just for curiosity, if you compare it with x of k, you can observe the first point 10 and 10 is in the same place. The remaining points, they are simply reversed. So this is a direct proof of how the time reversal property actually works. So reversing in time will reverse in the frequency domain also. Property number 5 is called as the circular frequency shift property. The statement of circular frequency shift property is something like this. If x of n has a DFT x of k, then x of n, the time domain sequence, when it is multiplied with an exponent e power of j2 pi by n mn, which could also be written as wn to the power of minus mn, both are same. Now, multiplying with an exponent in the time domain will cause a shift in the frequency. On the RHS, we see x of k minus m mod n. So the shift happens with the value which is m. Now, as you know, m here is a feature for the time domain. So n is present, n should be there in the time domain. The extra term that we have is m. So m here represents the shift. Now when the shift is equal to plus m here as per the notation, we get minus m in the frequency domain. Alternatively, when you go with the Wn notation, Wn raised to minus m, here also we'll get minus. So please stick to one notation and try to remember it. Circular time shift and circular frequency shift are opposite effects. In the case of circular time shift, we were shifting in time and there was a multiplication with an exponent in the frequency domain. Here, the exponent is multiplied in time domain and there's a shift in frequency. And please note the relationship between the signs also. In the case of time shift, when we wrote in the form of exponent, we observed the sign was same. Here the sign is opposite, because here if I have plus for m, here I'll have a minus. So find a method to remember the two properties well. Let us go for the proof of circular frequency shift. Now the proof goes something like this. Once again, we start with the definition of the DFT. In the definition of DFT, we prefer to write the twiddle factor in the exponential form because we know we are dealing with exponents here. So we'll change Wfn to be written in the exponential form. Now, since we know we are looking for the DFT of x of n into e power of j 2 pi by capital N mn. Let us do the substitution. So we replace x of n with that. Therefore, the DFT of this quantity, we see in the definition we have replaced x of n with x of n times e power of j 2 pi by n mn. Then the two exponents here can be combined. So we collect the common terms. We keep minus j 2 pi by n common because that's a feature of the DFT. And what remains is k minus m into n. So this arrangement has been used so that it looks like the DFT equation structure. Okay. So in the DFT equation, we are aware that we have e power of minus j 2 pi by n kn. So the change that we observe between equation 1 and equation 2 on comparing is the replacement of k with k minus m. Therefore, we can conclude that if equation 1 is called as x of k, then the equation 2 should definitely be called as x of k minus m. And we cannot simply write k minus m. Everything here is under the control of mod. Therefore, we apply a mod here. Hence, the proof. So this is the proof of the circular frequency shift property. Now let us check a simple numerical based on this. Now, if you know they are asking you to find endpoint DFT of a sequence called as x1 of n, which is x of n times cos 2 pi by n k naught n. We just note down the given. This is the given. Now cos, you know, can be split using Euler's relation. Cos theta is equal to e power of j theta plus e power of minus j theta by 2. And this is what you get. Then we have two terms now, x of n into the first exponent, x of n into the second exponent. Now we know that using circular frequency shift property, x of n, the first term, that is x of n into e power of j 2 pi by n k naught n, its DFT should be equal to, according to circular time shift property, it should be equal to capital X of k minus the shift. The shift here is k naught. So please observe the sign. Here we have plus, here we put minus, and again we have to apply mod of n. Also, the second term, what is x of n into e power of minus j2 pi by n k naught n will yield a DFT in a similar fashion as x of k plus k naught mod of n. Hence, combining these two results, see 1 by 2 here is a constant which we have not included up to now. So now we can put it. The final answer will be x1 of k equals 1 by 2 times x of k minus k naught mod n plus x of k plus k naught mod n. So this is a simple application of the property called as the circular frequency shift property. Property number 6 is called as the circular convolution or the time domain convolution. That is, we are performing convolution operation in the time domain. This result in a multiplication of the respective DFTs. So it's also called as frequency domain multiplication. We will learn a few differences between the linear and circular convolution. The primary change being that we use circular shift and folding or reflection is also done circularly. The rest of the steps will be the same. Let us take a look at the property. We have to consider two sequences, let's say x of n and h of n. Alternatively, people use x1 of n, x2 of n, that's also fine. Here we have taken x of n and h of n. The respective DFTs are called as x of k and h of k. Now, if you are convolving x of n with h of n, to indicate that we are doing circular convolution, we can put capital N within the circle, or we can use the symbol star, which is normally used for linear convolution, but if you enclose it in a circle, that becomes a symbol for circular convolution. So here we use N inside a circle as a symbol or star within a circle. Now, when you take the DFT of that, it becomes a very simple effect wherein we have to multiply the respective DFTs. So the more complicated task of finding a convolution becomes a simple job of finding the product in the frequency domain. This is one of the advantages of switching over to the frequency domain. Some tasks become easy. For example, convolution. Now, in circular convolution, we assume that the sequence are periodic. X of n and h of n both are said to be periodic sequence. Therefore, consider two sequence x of n and h of n of length capital N. Then the circular convolution is defined as, now the definition of circular convolution is shown below. Y of n is x of n star within a circle to indicate circular convolution. With h of n, the expression is something like this. Summation m is equal to 0 to n minus 1 x of m into h of n minus m mod n. Now, just for comparison, I have written the linear convolution expression here. First thing we see that the limits, it doesn't matter what you call the index, it may be m or k, it really doesn't matter because it's an intermediate value, it's a dummy variable. It's not a part of the final answer because the final answer is a variable of n. So you can call it any way you want. You can use m or k, it doesn't matter. So you see the limits here is between minus infinity to plus infinity, indicating that you can shift anywhere you like. You can shift to the extreme right, you can shift to the extreme left. But here the limit is between 0 to n minus 1. So since we are having a limited finite sequence which is periodic and which has a period is equal to capital N, it is sufficient that you consider the points between 0 to n minus 1. It is repeating. So it's enough to have between 0 to n minus 1. The second difference you can see here is, here we have simply h of n minus k, where k is telling about the reflection, because here we have k and we have minus k, so it's a reflected version. So h is folded, h of k is folded, and then it is shifted by the amount which is called as n. So here also we have x of m and we have h of minus m. That means we are doing deflection here also. And then we are shifting it by an amount called as n. So n here also sets the shift. But both these operations are controlled by mod. Other words, we perform the folding and shifting circularly. So this is one of the major important differences that you can observe. Now, to prove this particular property, I am interested in finding the DFT of y of n, which is nothing but the convolution between x of n and h of n. Symbolically, just for convenience, I am calling it as y of n. Therefore, DFT of y of n, which may be called as y of k. Now, we can substitute that y of n in the formula or the definition of DFT. So that becomes equation number 2. Now, since we already have an equation for y of n in the form of equation 1, let us replace that value of y of n. So substituting for y of n, you can see this quantity in the center, it's a replacement for y of n. Now, to proceed with simplification, first thing you can do is interchange the order of summations, bring out the summation with m outside. The term which depends on m, x of m, will also move outside because it only depends on m. The inner summation is n is 0 to n minus 1, h of n minus m mod n, w into the power of km. Now here, to proceed with the simplification, first the quantity which is the second summation, see structurally it's like a DFT equation. You see the summation, you see the critical factor, it's like a DFT. Other words, I want to know it's the DFT of the term h of n minus m mod n. Now the answer for this lies in a property that you have already studied. It's called as a time shift property. Now the time shift property will tell you that the DFT of this is nothing but h of k, because h of n's DFT is h of k, multiplied by the exponent. Okay, time shift. Okay, in the time domain if you shift, we have to multiply by exponent in the frequency domain. So here we are multiplying with wn to the power of km. Please note the sign also. Here we have minus, here we'll have plus. Therefore, substituting it here in the equation, this is what we have. And rearranging the terms, just rearrange the term. So you can write h of k on this side and wn on this side. Now this term also looks like a DFT. So this is the DFT of x of m, which we know is x of k. Therefore, the equation now reduces to x of k into h of k. So we have proved in a very simple way that convolution in the time domain, circular convolution in the time domain, results in multiplication of the DFTs in the frequency domain. This is called as circular convolution property, and it's a pretty important property also. The application of circular convolution property is that it is possible to determine the answer of circular convolution by using DFT and IDFT. It means that we know the method of calculating DFT of x of n. The result is called as x of k. We know the method of finding DFT of h of n. Result is h of k. These individual DFTs we multiply. This is as a consequence of the circular convolution property. So in the frequency domain, we multiply the respective DFTs. Now to change this back to time domain, we have to take the IDFT. So applying IDFT, we get the sequence called as y of n. The multiplication that is described here is called as element-wise multiplication. Other words, we multiply the respective elements. So for example, if we have 1, 2, 3 and 2, 3, 4, multiplication is between the terms 1 and 2, 2 and 3 and 3 and 4 results in a 3-point sequence. This method of calculating the DFT using DFT and IDFT, this method of computing the circular convolution using DFT and IDFT is called as the Stockham's method. We will solve numericals based on this shortly.
Thank you all.